So today's topic is on stable curves. It's the 14th lecture of the course. And I have pictured here an example of a stable curve. We'll introduce the definition formally, but you should sort of see through this example that it's condition that every rational curve meets the rest of the curve at least 3 points. And note that we're like writing these numbers here to indicate the sort of the geometric genus of the components. And we had this nice formula last time to compute the arithmetic genus of the total curve using, but you just take the sum of the geometric genus of the components, and then you add sort of the number of connected components bounded by this graph. And in this example, you get 14. Right, but before we can introduce stable curves, I want to give a quick refresher on our definitions. And so let's just review properties of nodes. So last time we introduced, so yeah, here C is a curve over a field. And in the case when it's algebraically closed, we say that a point is a node if the complete local ring has this, is isomorphic to the power series ring in two variables, mod the two axes, x, y. And then in general, it may not have this form. So you need to, you ask that there's a point in the base change to the algebraic closure, that there's a node over your given point. So maybe an example of why you need to consider these two cases is that if you take C as a curve over the real numbers, and you say mod out by x squared plus y squared, this is irreducible over R, but not over C, and so it's a node. And we see like after the base change, the node becomes what you might say split, i.e. the completion is isomorphic to this power series ring. And then, and then we say a curve is nodal if all points are either smooth or nodal. Any questions on that? Right, and then the main result we had last time is this local structure theorem, which tells you not just how nodes look like in a curve over a field, but also what they look like in families. So we have a sort of a general setup that we're considering just a morphism that's flat and finitely presented, where every fiber is a curve. And then if you have a point which is a node in the fiber, and in particular that means that the fiber is reduced at that point, then a tau locally you have such a diagram. And
I have a little.
Was there a question?
I have a little question, which is so when away from a node, this power series ring is just in one variable. Is that like this completion is just the power series in one variable?
Exactly. Yes.
Just checking. Thanks.
Yeah. That's an important point. That for a smooth point, the complete local ring is a power series ring in one variable. Right, and let's just spell out what this tells us in the case that the base is a field. Then this theorem implies that there exists. So an tau extension of a field is a finite separable field extension. And there's a point P prime in the base change such that the complete local ring, in this case of P prime, is isomorphic to the power series ring. And this was sort of a stepping stone of how we prove this theorem as well. We went from like understanding what the completion looked like in the fiber to the completion looked like in the entire family. And the basic example to keep in mind of what the structure theorem looks like for now in the relative setting. So for it is perhaps this example where you take x, y, and t over t. So here you have a one-dimensional family where when t is 0, the fiber just looks like the union of the two axes, but away from that, it looks like the hyperbolas, which are smooth. And what the theorem says essentially is that every deformation of a node, a tau locally looks like this, is the pullback of this example. Namely that there is, so maybe, yeah, let me just replace this k with a z so that we can really work in mixed characteristic. So what it says is then that there's a morphism from spec A to here, and then t pulls back to some function f, and then the base change is this spec A xy minus f. So a tau locally, your curve C looks like this particularly nice form. And maybe I wanted to quickly say that so here on the left-hand side, I reminded you what the theorem is and what we proved. And on the right-hand side, I sort of have a variant when the central fiber is non-reduced. So even if the central fiber is non-reduced, but let's suppose that your point in the reduction is nodal, then there's a similar sort of structure result. And I'm going to use this later, which is why I'm stating it. And I'm only going to use it in this restrictive setting where R is a DVR. And then you have a family of curves where the total family is regular, this map is flat and finitely presented. And so like we have these two different cases of whether if the point is smooth, then it essentially just looks like a thickened affine line. And then when it's a node, then you basically you can have exponents A and B inside here. So that it's like the central fiber is just, yeah, it's a union of thickened axes, perhaps with different weights. But we'll use that later when we discuss stable reduction. But maybe I should say one of the applications of this result for us is as follows. So we have this result, and I should point out that this is definitely more than we need. Especially for the applications I'm going to give right now. But the reason I'm including it in this form is because I find it like gives us a conceptual understanding of nodes and their deformations. And the proof is quite involved. And in fact, yeah, there were details that I didn't present last time. So certainly I'm going to revisit this argument when I look again at my notes. But I did want to spell out these two like nice applications of this. And the first is, let's suppose we have a family of curves, C over S, as in the theorem. So it's flat and finitely presented. And then let's look at this locus in the total family of points that such that the point in its fiber is either smooth or nodal. And then the claim is that this is an open condition in the total family of C. And to prove this, well, first let's know that if the point is smooth, we already know that the smooth locus is open. And so let's handle the case that if P is a node in the fiber. So here S is pi of P. Pi is the structure map. Then what this theorem gives us is this nice tau diagram up here. And so let's let this morphism from U to C be called G. And then you just take, then we've sort of arranged that this point is in, because G is a tau, if I take G of U, this is an open set inside C node. All right, so the theorem gives us much more, but in particular it implies smoothness. But in this condition, sorry, it implies openness of the nodal locus in the total family C. And if we want to get the openness of the nodal locus in the base, we need to impose a properness condition. So this is what I have over here. So if in addition, this is a proper family, then this nodal locus, then this locus of points S, so whose fiber is a nodal curve, is open. And this follows formally from the last one that this locus, nodal locus, is identified sort of with the complement of the non-nodal locus, and this is the image of this locus here. So this here is the closed locus in C of non-nodes. And then because pi is proper, this is also closed. Yeah, and that's it. And the reason we like this result is because at least this last corollary allows us to apply it to the moduli setting. So I've repeated, this corollary up here. Nodal locus in the base is open. And next time we're going to apply this result to show that sort of if I define the stack of all nodal, at worst nodal curves, so here objects are going to be flat, finitely presented in proper families such that every fiber is nodal. We're gonna use this to get that, to argue that this stack is algebraic. But there's problems with looking at all nodal curves. Even though it forms an algebraic stack, it's not separated. And it's not bounded. Here, I mean, it's not going to be finite type. And the reason for this sort of follows from the value of criterion for separating this. And so let's just suppose we have a family of curves degenerating to a nodal curve over a one-dimensional base. So this is like a spectrum of a DVR, like in the value of criterion for separating this. But what I can do is I can just blow up the node in this family. And what that does so I'm blowing up a point in the surface, and well, let's assume that the surface is regular. And what you get then is you insert a P1. So genus the zero curve. And so what we've constructed is another way to fill in that family of smooth curves over the origin with a different nodal curve. And of course, you could keep repeating. I could then blow up a different node, and then you're going to get a family with two P1s. And you can keep repeating this as many times as you want. And so you see that there's infinitely many limits of this smooth family over over the smooth family of curves. So it's definitely not separated, and you can even use this to show that it's not bounded. So this suggests we should restrict to a smaller locus, and this is the reason we're going to introduce stable curves. So that's our motivation for introducing stable curves, which we'll do on the next slide. I think this is a good time to pause for questions.
On the previous slide, or I guess on this slide even, in the corollary, do you have a quick example where I guess pi is not proper, and then we end up with the nodal locus in the base not being open?
I should. Wait. I should, but I don't. Yeah. Let me get back to you maybe after in the discussion section. And then, yeah. Okay, so let me introduce stable curves now. So here's our definition. Well, first I'm going to introduce pointed curves. So I'm not only going to introduce stable curves, I'm going to do it in the pointed setting. So we'll be able to discuss mg bar and mgn bar. And so an n-pointed curve over a field is just a curve, arbitrary curve. So a curve for us was just pure one-dimensional finite type scheme over a field. And then we just have an ordered set of points, k points. This is quite broad definition. And then we're going to say a point of a curve is special if it's either a node or a marked point. So we're going to treat marked points and nodes sort of on equal grounds. And so, yeah, now we get to the definition of a stable curve. And I should say, yeah, this definition was introduced by Mumford and Meyer in the 50s, early 60s. And I think there were some hints that this was a good notion coming from topology and other settings. I think even to Mumford and Mumford and Deligne, it wasn't clear whether this was the right notion and positive characteristic. And it was like, but after their seminal paper, sort of, yeah, I think we take this back for granted now that stable curves is the right notion and that they form sort of nice proper family, proper algebraic stack. Anyway, so here's a definition of a stable family, of a stable curve. So it's an n-pointed curve. And so we have our usual assumptions that C is connected, nodal, and projective. I should say geometrically connected over a non-algebraically closed field. And then our points are distinct and smooth. So these are important hypotheses, distinct and smooth. And then we have these two conditions, 1 and 2. First one is that every smooth rational subcurve contains at least 3 special points. And then there's no, that C itself is not a genus 1 curve with no marked points. I think it's best to look at this as in examples over here. Maybe we should first look at these bottom curves here. These are all not stable. And like in this case, this is not stable because it's a genus 1 curve with no marked points. We don't want to include that. And in this case, you've marked a node. You don't want to do that. In this case, your 2 marked points are equal. We want to disallow that. And here, in this case, we have a rational curve, subcurve meeting only at 2 points. And yeah, and we disallow that. On the other hand, up here are all examples of stable curves. And in these diagrams, I only put the geometric genus 0 if it's to remember that it's a rational subcurve. And so to note that in these definitions, there do not exist stable curves if Gn is equal to 0, like is it 0, 0, 1, 0, 2, or 1, 0? And this is equivalent to this numerical condition that sometimes we impose that 2g minus 2 plus n is less than or equal to 0. So we sometimes impose g minus 2 plus n. Sorry, this should be 0. Is greater than 0 in order to avoid these special cases, in order to ensure that the moduli stack is non-empty. Any questions? Yeah, so this is one of the critical definitions for the remainder of the course. And my goal today is to motivate this definition and show that it has some nice properties. But let me just explain first some variants on this. So here I've defined stable. I can also define semi-stable, where I replace the number 3 with 2 in condition 1. So for instance, this example on the right-hand side is pre-stable. Oh, sorry, is semi-stable. And then you can also call a pre-stable curve where you just drop 1 and 2 entirely. So it's essentially, it's just a nodal, it's just a proper connected nodal curve with distinct and smooth points. Right, and so clearly stable implies semi-stable implies pre-stable. Okay, so the first property I want to show is that that being stable is well behaved with respect to the pointed normalization of the curve. So let's start with, let's just take here, let's take C to be an n-pointed pre-stable curve over a field. So again, that means already that the points pi are distinct and smooth in C. And then we take the pointed normalization C tilde and note that, since pi is smooth, its pre-image under the normalization is there's a unique point. And let's let the pre-image of the singular locus be denoted like this. So these are all the points in C tilde over nodes. And the first exercise that I suggest is to show that C is stable, the C is stable if and only if every connected component of the pointed normalization is stable. And rather than proving this, I'll just give you an example. So let's suppose we have our curve C, and then we'll take the normalization. Suppose our curve C has 3 components. Suppose there's a curve like this, and then in red there's this, and then there's a rational curve. This maybe, and with a marked point here. But if you take the normalization, then there's 3 components. And on the blue component, the pointed normalization is going to have 4 nodes, right? This gives you 2 points, and then there's these other 2 points. Well, I could even, let's just assume this is his genus 4, this is genus 2. And then, yeah, and the red component is going to have how many points? 1, 2, 3, also 4 points. And the key here is for the rational subcurves, and this purple one also has 3 points. And so it's stable, both the curve itself and its point of normalization is stable. All right, and so we're after sort of an equivalent characterization of stability for pointed curves, and one of the facts we're going to rely on is the following property for smooth curves. The only smooth n-pointed curves, C P1 to Pn, with the automorphism group infinite, are the following. Well, first I should tell you, yeah, in the pointed case, what do I mean here? This parameter has automorphisms of C with such that that preserve the points. So automorphisms of pointed curves preserve the points and their ordering, right? It doesn't move around the PIs. It fixes each PI. And so the only curves with positive dimensional with infinite automorphism groups are either P1, where n can be 0, 1, or 2, or C is a genus 1 curve, and n equals 0. And again, these are sort of the same conditions we saw earlier, that 2g minus 2 plus n is less than or equal to 0. And so we're going to use this fact to prove the following proposition. So it's an n-pointed curve. N-pointed, pre-stable curve. Then the following are equivalent. One is that it's stable. Two is that the automorphism group is finite. And three, the dualizing sheaf, which we introduced and gave an explicit description for last time, twisted by the points, is ample. So this gives you 3 different ways to think about stable curves, and they're all, I would say, equally important. This isn't a difficult fact, so let's just, in fact, like 1 and 2, we've basically spelled out. They follow from the exercise on the left-hand side and the fact above. Right? The only way that you can have that you can have infinite dimensional automorphisms is if you're either a P1 or a genus 1. And these are like exactly the conditions we removed, that we imposed in the definition of stability. For the equivalence with 3, we need to use one property of the dualizing sheaf that I didn't mention last time. So let me say it here. We're going to use the following fact, that if C is a nodal curve and T inside C is a subcurve, then if I take omega C and I restrict it to T, it's the same as omega T twisted by the intersection points where T meets the rest of the curve, namely where T intersects its complement. So maybe on the left-hand side here, like if T is the blue subcurve, what this implies is that omega C restricted to T is omega T shifted by these 2 points, say Q1, Q2. Right, and so I'm going to now use this fact. So therefore, let's understand when is this line bundle ample? Well, the normalization is a finite morphism. So this is the same as the pullback being ample. But you know, the normalization is just a disjoint union of its components. So this is the same as saying for all connected components of the normalization that omega C restricted to T should be equal to omega T. Well, by this formula, this is the same as omega T. And now I only need to remember, I should only remember the points on T. And then I need to remember the intersection. And so this then is in turn equivalent to saying that for all these connected components that T and the shift, okay, this is running out of space, is stable. And the final observation we need is that, you know, if I look up here at this fact I had for automorphism, for the finiteness of the automorphism group, is that this is it's the same property, the same is true for ampleness of omega C shifted by these points. Just this is the basic property of smooth curves that we know that, you know, if that just on smooth curves, we know that if you have a line bundle whose degree is positive, then it's ample. And so this just boils down to a numerical condition because we know the degree of the dualizing sheaf is 2G minus 2, where you twist by these points n. And so the only way that cannot be ample is either if the curve is P1 with 2 or less marked points or genus 1, in which case the dualizing sheaf is trivial. Right, so that I think that wraps up these three conditions. Questions? Yeah, if you're interested in higher dimensional geometry, I think it's like every aspect of when you try to define moduli of higher dimensional varieties, there are issues, and so I think you should, yeah, in sort of define like defining stable families and defining dualizing sheets, and there's a lot of issues. The case of smooth of curves is sort of the nicest, where and we have really three ways to think about stability. Okay, so we know for a stable curve that if I take omega C and twist by these points, it's ample. And just like with smooth curves, it's useful to know when it's very ample, because then you can use this embedding for a variety of reasons. So I'll just leave this as an exercise. But I'll tell you essentially the strategy to do it. So we want to know that for a stable curve, that if I take a sufficiently high power of the dualizing sheaf twisted by the points, then it's very ample. And let's, in this hint, let's just assume n is 0 for simplicity. Just it makes the notation easier. And what we need to show is that omega C twisted by k separates points and tangent vectors. So that is, if you just spell out what this means, to separate points, you need for all points x and y of C, you need that there's enough global sections of omega C twisted by k so that this surjects onto so you need to show that that's surjective. And the second one is for all points then x and C that you can separate tangent vectors. So you need enough sections so that it surjects onto omega C tensor k, tensored not by the residue field, but by the second power of the maximal ideal. So OC mod second power of the maximal ideal. Whoops, that should be X. All right, and now now you realize that both A and B come from an exact sequence in cohomology. Namely, I have omega C, and I can tensor it with the maximal ideals of X and Y. And this sits inside this and then maps to the quotient. And A and B come from the global sections of this. So you see that it suffices, right? We need to show that H0 of this is surjective. So it suffices to show that H1 of C omega C tensored with K, tensored MX and Y equals 0. And now here, this is for all X and Y in C, but actually possibly equal. So we've merged these two cases into this one vanishing of cohomology statement. But it involves the dualizing sheet, so you can use, we can relate this to the Serre duality to the vanishing of the homomorphisms from MX and Y into this. And now the exercise is to show that this vanishes using sort of a case analysis of whether X and Y inside C are nodes or smooth. I think my next topic, I'm going to move on to like families of stable curves. So it's a good time for questions or comments if you have any. All right, so far we've just discussed stable curves over a field. Let's now move on to families of stable curves. So I've saved time by writing the definition here. And here, so last time I discussed nodal curves, and we even had results about families of nodal curves, but I didn't define what a family of nodal curves. And in the literature, when people use the word family, you should really ask exactly, you should look to see exactly what they mean. I mean, a family should always mean flat, but then whether you include it to be proper is up to you. So, but for us, it will include it. So for us, a family of n-pointed nodal curves is going to be a flat, proper, and finitely presented morphism of schemes such that every geometric point, together with n sections, such that every geometric fiber is a reduced connected nodal curve. No, I have no conditions on whether these sections intersect or whether they land in the smooth locus. So this is not the fibers are not necessarily the pre-stable curves that I defined. But now for stable curves, a family of n-pointed stable curves is simply a family of nodal curves such that every geometric fiber is stable. So that ensures that the sections are disjoint, that they land in the smooth locus, and that every fiber is stable. And we can give the same definitions if we want for semi-stable and pre-stable. But now that we have this definition, we can define MGN bar as the pre-stack, where the objects of MGN bar are families of smooth, stable families with n sections. Stable families, and stable n-pointed families. And right, this is the stack over, the category of schemes, right? And this object lives over the scheme S. And morphisms are equal to Cartesian diagrams preserving the section. Great, and you can check that yourself that it's a pre-stack. I mean, And just like with families of smooth curves, on the right-hand side, I have this nice property of families of the analogous property for families of stable curves. But maybe to set this up, I need to talk first about the relative dualizing sheaf. And so here we just use this there's this fact. Depends what you want to use here. But if you have a pre-stable family, or even a family of nodal curves, then C to S is a local complete intersection. And this implies that there exists a relative dualizing sheaf. And maybe for this isn't in Hartshorne. It is in one of Hartshorne's book. So maybe the reference is Hartshorne, but his Residues in Duality book. But in a more elementary way, it is in the introductory text by Liu on algebraic geometry and arithmetic curves. So it kind of works just like the dualizing in the absolute case over a field. And the main property you need to know is that if you have sort of a family of curves over S and a base change, then if I take the relative dualizing sheaf and I restrict it, and I pull it back to CT, it's isomorphic to the relative dualizing sheaf. In particular, if I take the relative dualizing sheaf and I restrict it to a fiber, then I get the relative dualizing sheaf of that fiber. Ooh, okay. So I won't really say much more about this existence or properties. That's a whole other topic. but I will mention the following, the proposition that's written there, that is that the relative dualizing sheet is, so let me walk you through this. So I have a family of n-pointed stable curves of genus G, and then I take the line bundle, which is the twist of the relative dualizing sheet by the sections, and because we're assuming the sections land in the smooth locus, this forms the divisor. So this is legitimate. Then and then since k is greater than or equal to 3, if k is greater than or equal to 3, then the statement is that this is relatively very ample, and moreover that the push forward is a vector bundle of a given length. And in fact, the reason this is true is the same way we prove this for smooth curves. Like this, for the relative very ampleness, this condition can be checked on fibers, and that's what we proved on the last slide. To get that the push forward is a vector bundle here, you use, this is a standard application of cohomology base change. And then to get at this number here, this is just a Riemann-Roch calculation.
So can I ask you something?
Mm-hmm.
Already in the case of smooth curves, so what is the global map to, and we have the curve C, and we want to embed C inside the sum P of epsilon, say, that is this shift. How is this map defined globally? Meaning, if I have just one curve, this is, I take a base of the sections and, okay.
Yeah, are you saying that what I think it works the same as with smooth curves, right? Like if you have your curve C over base, you do this construction, and it embeds into the projectivization of the push forward of this line bundle twisted by K.
Yes, and my question is, how is defined the map from C to P? How is that map defined?
Oh, this just follows from, are you comfortable with how it's defined when S is a field?
Yes.
Well, I think it works just the same. You need to know, there's an analogous fact for, if you want morphisms to relative projective space, they correspond to there's a functorial description of this relative projective space, and I don't want to get into it right now, but it follows in a similar way that as if S is just a point. Right, you use the functorial description of relative projective space.
Okay, then.
Yeah, I don't want to go into all the details right now because it would be a bit of a detour. And in fact, I don't even want to use that. I'm not going to use this embedding. Maybe you were sort of ahead of the game and you're suggesting, like the way we proved that MG was an algebraic stack was using these this property of families to embed MG to express MG as a quotient stack of a certain Hilbert scheme mod a PGLN. We could do the same for MG bar and MG n bar, but we're gonna proceed by a different method. So and in fact, the way we're gonna do it is we're gonna show that the entire stack of curves is algebraic, and then what we need to know is that the nodal locus is open. Oh wait, actually, we know that the nodal locus is open. We need the refinement that the stable locus within the nodal locus is open, and that's what I want to get to next. So we need openness of stability for families of nodal curves. And so I take a family of n-pointed nodal curves, and I want to argue that the locus of points in S such that the fiber is stable is open. We first realized that the locus where these points are distinct and smooth is open. So this allows us to assume that C to S together with the sections is pre-stable. And now I'll give actually two different arguments for why it's open using two of the characterizations for stability. The first is going to be using the automorphism group. So I take the relative automorphism group, C over S, preserving the sections sigma 1 to sigma n. This is a relative group scheme over S. So here I'm going to use that this is a finite type group scheme, which you need to show. It's a separate argument. I'm going to skip that here. And since it's a group scheme, there's a section here. So the normal semi-continuity arguments actually imply that if you look at the function from just the set S to Z, that takes a point to the dimension of the automorphism group of that fiber, then this is upper semi-continuous. And what that implies is that the locus where that dimension is 0, so S in S, such that CS sigma I S is stable, is identified with the locus of points S where where the dimension is 0. And therefore this is therefore it's open. And the second condition, I could have also, rather than looking at the finiteness of the automorphism group, I could look at I had this family of curves, and I could look at L, which is the relative dualizing sheaf. And I know that ampleness is an open condition. Well, actually, let me twist by the mark points. And then, so the condition that S, such that LS is ample on CS, we've showed that this is exactly the locus where the curve is stable. And so again, we get that it's open. Any questions? I think I'm actually doing well for time today. I have one more topic. Yeah, and what I'd like to discuss is automorphisms, deformations, and obstructions for stable curves. And so this is our last topic today. And like you know, for the automorphisms, the deformations, and the obstructions, you know, for a stable curve, just like any variety, are governed by these groups, by these X groups. And what I want to show is that we can calculate the dimension of these X groups for an n-pointed stable curve. I know what X0, X1, and X2 are. And we're gonna use this later. We're gonna apply this because if x0 being 0 implies that there's no infinitesimal automorphisms. We already know that the automorphism groups are finite, but this tells us that they're even non-reduced. And that was the condition that's going to allow us to conclude that MGN bar is Dn. And if the x2 being 0 tells us that there's no obstructions to the forming. And I'll spell it, I will spell it again. When we actually apply this, I'll spell this out more precisely. This implies via the formal lifting criterion for smoothness that MGN bar is smooth. And x1, because it's smooth, we can calculate its dimension as by computing the tangent space. And the x1 calculation will tell us that the dimension of MGN bar over a field is equal to 3g minus 3 plus n. So that's the reason we're doing this calculation. But today, all I want to compute is, I just want to compute the dimensions of these groups. And I'm gonna do it again just for simplicity. I'm gonna make the assumption that just because I don't want to keep writing all the mark points, I'm gonna take n equals 0. And so I'm gonna first prove the I equals 0 case, and repeatedly in every step of the argument, we're gonna sort of use this picture here. I take the normalization. This sigma is the set of all nodes, and sigma tilde is its preimage. And we view like C tilde with sigma tilde as a pointed normalization. Where I'm sort of, when I write that, I'm sort of implicitly assuming an ordering of sigma tilde, an ordering of the points in sigma tilde. Right, so what we need is the claim here. We need to identify, the claim is that that there's an identification that homomorphisms from a big omega C into OC are the same as homomorphisms from the twisted sheaf of differentials to OC tilde. In other words, what this says is that regular vector fields on C are identified with regular vector fields on C tilde vanishing at preimages of nodes. You can show this directly just using properties of the sheaf of differentials and how they behave under push forward and pull back under the normalization map. But I'm gonna skip the calculation here. I'm gonna skip the claim, skip the proof of the claim, and just tell you how we use the claim. So the claim implies the following: that if that sense. One of the critical hypotheses here is that we're starting with an n-pointed stable curve. And by that exercise, we know that the pointed normalization is also stable, or each connected component is stable. And this implies that H1 of that there's an identification of this group here with what I'm writing here, H1. The point is that the reason we work on the normalization is that omega C becomes a line bundle. And in particular, then I could take it to the other side. And so this is identified with H0 of T C tilde twisted by negative tilde. And this is 0 because the degree of this is, because it's stable, the numerics imply that the degree of this is less than 0. Okay, that was the I equals 0 case. Okay, we're going to jump to I equals 2 and then move to I equals 1. So we're going to have to compute, we want to show vanishing of x2, and we're going to use a spectral sequence. I think it's the only time in this course we'll use a spectral sequence, but it's a relatively simple one. So we're going to use the following local to global spectral sequence of x and the Sheafy x.
Sorry,
Yes.
can I interrupt you? Is there some assumption on G? Because, for instance, if I take C to be smooth, for instance, I think P1, is that 0?
Well, no, there's no condition on G, but the condition is that the pointed curve is stable.
I see. Okay, sorry. Yes.
So yeah, like if you do this calculation, the same thing won't hold for just P1 with no marked points.
Yes, thank you, sorry.
Right, so we have a local to global spectral sequence where on the E2 page, the PQ, I take HP of the Sheafy XQ. And the fact we're using is that the spectral sequence degenerates to XP plus Q, right? And this is what it converges to is what we're trying to compute. And we're going to use, and we're going to compute the individual terms on the E2 page. And the first observation, which I've already written, is that since the dimension of C is 1, all cohomology vanishes when P is greater than 1. So E2PQ is 0 when P is greater than 1. So I've drawn this, the spectral sequence here. So we have vanishing to the right. This is all 0. And I think if I get the arrows right, I think that the maps go down to the right. And actually we already know that this group here is 0. We've computed that. And to compute I equals 2, the relevant information is on these two terms, right? This is the interesting stuff when I equals 2, because these give you the factors of the filtration of the x2, essentially. Right, and so let's see if we can compute them. Let's first look at E2 1, 1. That's H1 of C of Sheafy X1 of omega C OC. Okay, and I actually claim that this thing has dimension 0 support. Because first of all, omega C is a line bundle away from the nodes. And so therefore, like if I take C in Z and this fact that if I take, this is a sheaf on C, if I localize the X sheaf at Z, it's the same as computing the local X groups. And for points, if Z in C is smooth, then this is a line bundle and this X group vanishes. So that you're only getting, so it's only supported, this X1 sheaf is only supported at the nodes. And therefore, if you take H1 of it, you get 0. Okay, now we need to look at E21. Now we need to compute E220. And we're going to use the fact that, yeah, since C is a curve, and nodal, it's a local complete intersection. And this implies that there exists a locally free resolution, maybe like this, of the sheaf of differentials on C. Maybe I should say explicitly, what you can do is, like, if you have a point P in C, which is what you can find an open subset of C and an embedding into side AN defined by an ideal sheaf I, and then you have that omega on U is surjected by the restriction, and its kernel is exactly I mod I squared. Or if you prefer, you can even do this calculation formally locally, and then you can use the fact that we know exactly what the formal local ring is at a node, and you can just compute the relative sheaf of differentials of the structure sheaf of that, that complete local ring, and you see that there's a two-term resolution. But that's good for us because we want to compute this term is what is H0 of sheafy X2 of omega C OC. And what this tells us is that this sheafy X2 just vanishes. And so that we get that this term vanishes. And altogether, this is implying that X2 omega C OC is 0.
I think that the indexing might be a bit wrong, unless I'm confusing myself. Like
of the spectral sequence.
Yeah, like E20 should be 0 just because like P equals 2 is greater than 1, right? Like, should it be E02?
Oh yes. Oh yeah, great. Yeah, the indexing is wrong. Yeah, this is 02. Right, we're after. Let me highlight it over here. We're computing what's in the green here. It's E202, and so this is also. I think that was the only mistake, right? In the indexing.
Oh yeah, I think that's right then. Okay, yeah, it makes sense.
Thank you, Grant. All right, one calculation left. It's the I equals 1 page, and. So for the I equals 1, maybe I'll highlight it in purple, are these two guys. So this is what we need to understand with I equals 1. In fact, they're both going to be non-zero. But what we can use is that, the low degree terms of the spectral sequence gives us a nice exact sequence. Namely, it gives us the following. So what that spectral sequence gives us is an exact sequence like this, what's written out. And let me just write down explicitly what this one is. This is the H1 of the sheafy X0, or of the hum. This is H0 of sheafy X1. Okay. And so let's understand this, sort of term by term. Oh, we also know that this guy, the term on the right vanishes. This is 0. And on that last page, we also showed that this sheaf here has dimension 0 support. And since you're taking global sections, that's the same as taking global sections. I could just take the product over all the nodes. So I'm carrying, up in the top right corner, I sort of recall the basic setup. The sigma is the set of nodes, sigma tilde is its preimage in the normalization. So if Z is a node, yeah, this is exactly the H0 of X. This is just X1 of omega C Z localized at Z. Are you with me so far? And so, yeah, this is the local X calculation. But I could, if I want, I could also complete this. This is, there's an identification like this as well. And this completed sheaf of differentials is equal to the sheaf of differentials of the completion. Okay, and now, so yeah, and I'm going to now relate some of these terms to infinitesimal deformation theory. So we know that this group here, this X1 group, classifies first order deformations of C. And so what we mean by that is just a deformation over the dual numbers. So an element of this group can be thought of, here I have C over my field. I can include into the dual numbers. And I could, suppose I have a flat family in a Cartesian diagram. That's an element of this X1 group. So I'm using the facts about first order deformation theory. But note that on the right-hand side, this X1 group is of the same form. It's X1 of the relative of the sheaf of differentials and the structure sheaf. So this corresponds to first order deformations of the singularity of the completion of C at Z. And what this map is, and this is, you can identify this map where this takes this map to the first order deformation, which is of the singularity. Where now I complete the total family of C, of script C at Z. Great. Okay, now, so I have a short exact sequence, and I have this interpretation in terms of deformations. And so that allows me to think about this kernel on the right-hand side here. I can identify that with first order deformations. So this is first order deformations of C that preserve the node. But we have another description of that as that first order deformations that preserve the node induce first order deformations of the pointed normalization. So this is equal to first order defs of the pointed normalization, which is identified with X1 of, let me write it here. X1 of omega C tilde shifted by sigma tilde of OC tilde. These are equal. Ooh, okay. And now to wrap up, so yeah, the upshot here is I have a short exact sequence, just keeping the most important terms. And my goal is to compute, this is my goal. I need to compute this dimension. And the way I do it is by computing the two terms. Let's do it. Let's first start with the right-hand side. So each of these X groups is one dimensional. This is just like, you can do this as a local calculation using a resolution of the sheaf of differentials of the complete local ring of a node. And therefore this whole group is just, his dimension is the number of nodes. All right, so the tricky one is the left-hand side, this group. Well, but the point is that, this is a line bundle. So we can, because we're on the normalization, we can compute its dimension. Well, let's do it carefully. So this dimension. So to do it, I'm gonna do it on the components separately. So C tilde is the disjoint union of connected components C tilde I, and let's let sigma I tilde be the restriction of sigma tilde to C tilde I. And then the X group is just the sum of the X over the connected components. So this is the sum over the connected components of X1 of omega C tilde I shifted by. Okay. And here we use that it's a line bundle to identify this with H1 of T. Right, and now I could use Serre duality. Okay, there's several ways to do this calculation. I'm just choosing, this path. It's not necessarily the the minimum number of steps. But if I use Serre duality on this H1, then this is H0 of omega C tilde I tensor 2 shifted by sigma tilde I. I mean, I could have just applied Serre duality to the X1 if I wanted. But now I can apply Riemann-Roch to this. Because this thing has positive degree, there's no H1. So Riemann-Roch tells me that this is just the sum over I of the degree of C tilde I tensor 2 shifted by the degree of this. So everything in parentheses plus 1 minus the genus. So I'll write this as GI. This here is the genus of C tilde I. And the degree of the relative sheaf of differentials is 2 times the genus minus 2. I multiply that by 2. So I get like 4 copies of a G minus 1, but then I'm subtracting a G minus 1. So I'm left with sort of the sum over I. So inside here, I have 3 G tilde I minus 3. And then I have the size, how many points are over nodes in C tilde I. Okay. And then, so this calculation, this then becomes, okay, I have 3 times the sum of G tilde I over I. And then I'm subtracting 3 a bunch of times. I'm subtracting 3 exactly the number of times of the components. And note that for every node, there's 2 preimages in the normalization. And since I'm summing over all the connected components, the part that this gives me as I sum over I exactly 2 times the number of nodes. Whew, okay, so I got the left-hand side and the right-hand side, and this to wrap it up in green, I get that the dimension of this is equal to 3 times this sum minus 3 number of components. Okay, let me plus, and on one hand I have 2 nodes coming on the left-hand side, and then another number of nodes on the right-hand side. So I get plus 3 times the number of nodes. And then, by the genus formula, this is 3G minus 3. Because by the genus formula, G is the sum of the G tilde I's minus the number of components plus the number of nodes, and then there was a plus 1. So I think everything works out and you get 3G minus 3. And so this gives us the dimension of mg bar even over the locus of stable nodal curves. I'll end